Hello everybody! Today we're going to be talking about one of my favorite topics, software design. And we're going to be going over some principles from the author of my favorite book on software design, which is A Philosophy of Software Design, and his name is John Ousterhout. So this is going to be our content. We're going to go through it all. I'm just putting it on the screen here so you can take a look at it and be aware. But let's just move on because we're going to go over each of these pretty in-depth. So who is John Ousterhout? He's a PhD in computer science from Carnegie Mellon in 1980. He's a professor of computer science at Stanford. He founded the company Electric Cloud in 2002. He created the Toctical scripting language. He led the research group that designed the Sprite OS. He led a team that created the first LOD structured file system. And he won the Grace Murray Hopper Award for his work on large-scale integrated circuits, and was inducted as a fellow to the Association for Computing Machinery for the same reason. Suffice to say, he's a prominent and extraordinary engineer. He is presently offering a course at Stanford, which I would love to take, but I am not presently taking, so this is not a discussion on that, but it essentially aims to teach the skills necessary to be a 10x developer. And as I mentioned, he is the author of my favorite book on software design that I have yet read, from which much of this presentation is drawn. So let's start by defining the big bad that we are trying to deal with, which is complexity. Complexity is anything related to the structure of a software system that makes it hard to understand and modify that system. It consists of three elements: change amplification, cognitive load, and unknown unknowns. So change amplification is when simple changes require code modification in a large number of places across the code base. So pretty basic example, let's say you have a website that has many different pages on it. And on the top of every single one of these pages, you have the same banner that gives like welcome information or whatever, right? And but instead of reusing the same component over and over again, just like having JavaScript that generated it or something, you actually have specific HTML that you have just copied and pasted hundreds of times across your code base. Now your designer lets you know, hey, we need to make a change to this banner. Oh no, you have to do a lot of find and replace in your code base in order to do this. So this is change amplification. So reducing change amplification means reducing the amount of code changes that are necessary when you make design changes in the code base. Next is cognitive load. This is how much a developer needs to know in order to complete a task in the code base. Now, this isn't necessarily correlated with lines of code, though it can be, but in situations where reducing the number of lines of code will obfuscate the functionality that code is doing, more lines of code would actually decrease cognitive load. So some basic examples: bubble sort, very easy to understand sorting algorithm, but it requires a large number of computer resources. Quicksort is a much more difficult to understand sorting algorithm, but it requires far fewer computer resources. So this is a place where you're making a trade-off. Do I want my code to be easier to understand, or do I want the computer to be able to run it more efficiently? Another example, if you're familiar with React, if you are managing state just inside of your component, then that is very easy to understand if you are only concerned with that particular component. But if you need to have state that is being managed across the entire application, you need to do a lot of prop drilling. You're passing methods up and down in props, and it gets very complex and very difficult to understand. By contrast, the context API is something that if you are trying to manage local state doing it, it's going to be very heavyweight. There's a lot of, there's complexity there of wrapping the state around the component that you want to do, making sure that it is accessible, the additional lines of code necessary to make it work, right? All of that is increased local complexity. However, it is much easier to have the context API available to many different components in distantly related locations of the code base. So it is globally simpler, but locally more complex. And these are the sorts of trade-offs that you need to make, that you need to think about when you're doing this sort of software design. So the third is unknown unknowns. This is when it is not obvious what code needs to be modified in order to complete a task. In other words, there is something that you need to know in order to make the change you want to do, but you don't know that you need to know it, and when you fail to make that change, there is no indication that there is any problem at all. This is the worst of the three, because this is the stuff that inserts bugs into your code base and causes problems and will, over the long term, completely destroy your app and make it completely unmaintainable. This is the death by 1,000 cuts sort of situation, which is why it's so important to avoid. An example that I've run into in the past is when you are doing state management with Redux. At the beginning, it makes global state management very easy, but as the app gets more and more mature, you update state in one component, and then another component that you had no idea was involved with that whatsoever winds up getting affected by it and broken. And this is why a lot of people have criticized Redux for its opacity and its complexity, because it can cause so many unknown unknowns if you're not extremely disciplined in how you work with it. So let's talk about some causes of complexity. The causes of complexity that Ousterhout discusses are dependencies and obscurity. So a dependency is present when a given piece of code cannot be understood and modified in isolation. It relates to other code that must be considered before a change can be made. So you can usually think of dependencies as like the parameters that are being passed into a function. You need to understand what is being passed into those parameters in order to understand how a function is going to behave. So ideally, we'd like to reduce the dependencies and make the dependencies that are present in our module as clear and simple as possible. And indeed, one could say that much of software engineering can be described as the management of dependencies. Obscurity is a lack of clarity on how the code behaves, so this can be caused by any number of things, including generic variable names, just having one letter being used for a variable name as opposed to a descriptive variable name, a lack of documentation, a lack of comments, a lack of meaningful unit tests, using the same variable name in many different instances. These are the sorts of things that can make your code more confusing and thus more difficult to maintain. So dependencies lead to change amplification and cognitive load, while obscurity leads to unknown unknowns and also contributes to cognitive load. And it's also very important to understand that complexity is incremental. This is not a single big mistake that you're ever going to make while working on your code base. It is the accumulation of hundreds of little errors over a very long period of time. You can sort of think of this as like managing your health. Eating lots of junk food versus working out. Usually not the big mistake that you made that is going to kill the code. It is the thousands of tiny little increments of complexity that you fail to address and be disciplined about. So let's talk about two ways of approaching programming: strategic versus tactical programming. So tactical programming is probably the most popular style, and it is focused on getting the new feature to work. We need to finish this job as quickly as possible and just get it shipped. Okay? When you are making changes to the code base, when you're refactoring something or modifying some code, the goal is to modify as little of the code as possible. When you are programming in this way, each added feature adds a few small complexities to the code base. You can get away with them in the short term, but they accumulate and become more and more difficult to deal with in the long term. And the worst offenders of this are what Ousterhout calls tactical tornadoes. These are developers who deliver features faster than anyone else in the company, but they leave behind them a tremendous, terrible layers of added complexity. And it's especially pernicious because management will view these sorts of developers as the heroes of the company. When there's something that's really important to be done, they're going to put that person on that task to make sure it gets done quickly. But in the long run, they're actually undermining the company and may well be the reason that the application fails because it's impossible to maintain. The other side is strategic programming. Working code is not enough. It must also be designed well. It is not acceptable to introduce new complexities in order to finish a task faster. And this requires an investment mindset. We are working for the long term. And I want you to keep in mind that when I'm talking long term here, some people have this idea that it's like really, really long term, like years out. I don't think it takes that long for the effects of tactical versus strategic programming to hit. In my experience, it's on the order of like 3 to 6 months that the velocity of the team really starts to grind to a halt because of how much tech debt has accumulated in the code base. So this isn't like some far off thing. This is a little bit more immediate than you might think it is. So let's start talking about how to deal with some of this complexity and how to reduce it. And first, let's talk about interfaces and modular design. So the goal in modular design is to design a system so that developers only need to face a small subset of the system's complexity at any one time in order to deliver a new feature. So ideally, you should be able to open up a file, deal with a particular module, and not know hardly anything at all about the rest of the system and still be able to effectively deliver this new feature. So the software system as a whole is divided into a collection of these small modules, and then these modules the system is decomposed into services, subsystems, classes, and all of which we can sort of categorize as different layers of modularity, right? So the idea is you're just trying to keep your system encapsulated so that the amount of knowledge about the system that you need to carry in your head at any one time is as small as possible. So modules can typically be divided into two concepts, the interface and the implementation. The interface is everything the developer must know in order to use a given module, while the implementation consists of the code that carries out the contract implied by the interface. And then the dependencies between modules are the incoming parameters from outside the module. For example, arguments in a function. So one way in which you're probably very familiar with this is when you were using libraries. You bring in a library and you read the documentation on how to use this library. That documentation is informing you about the interface of that library. This is how you use this new library that you are incorporating into your application. Generally speaking, if you're in a situation where you need to start looking at the source code of the library that you have brought in, it's a failure of the programmers of that library. Ideally, you should only need to understand the interface in order to properly employ it. So a deep interface is when you have a simple interface that provides access to a very complex implementation, minimizing the complexity of the module that it imposes on the rest of the system. So my favorite example of this is a light switch. You flip this light switch and think about all of the complexity that lies behind that system. There is maybe a nuclear power plant that is behind that light switch that is providing light to your apartment or your house, right? Think about all of the wires. Think about the system of electrical components that are lying behind that light switch, and all you need to do is just flick it on and off in order to get the desired benefit. Incredible interface. Meanwhile, a shallow interface is when the interface is nearly as complex as the implementation it provides, or even more so. So here's an example. Set value of object at key, which accepts an object, a key, and a value, and then sets that key to that value. Calling this function takes more keystrokes than if you had just done what the function does. So that's an example of a shallow interface. Here's another example of a very beautiful, deep interface. The input and output operations in Unix. So we have 5 functions here. 5 simple lines of interface code with hundreds of thousands of lines of implementation underneath it, managing efficient file access, directory storage, permissions, file caching, and everything else that Unix does. Absolutely incredible design right here. So moving on, let's talk about a concept that Ousterhout introduces called classitis. Classitis is the notion that all interfaces need to be small. You might look at a function and say, your function has too many lines, your class has too many properties or methods, or perhaps you will articulate a hard limit on the number of lines of code you're allowed to do. Maybe if you ever have more than 20 lines of code inside of your class is too complex and you need to break it up. The problem with this is, by following such advice, people often wind up creating a large number of very shallow interfaces. And because you're arbitrarily splitting up your code and just splitting into a whole bunch of different files, you are increasing cognitive load. You are making it more difficult for a developer to understand the code you have written than if you just kept all related code in a single location. And this is commentary. This isn't Ousterhout. This is me. But in my experience, classitis is something that often emerges from naively and dogmatically applying solid principles. We're going to get into Clean Code, another video. Fantastic, wonderful book. But if you implement everything that is in Clean Code without an understanding of the sorts of things that are discussed in a philosophy of software design, you will become a worse developer because you will make these really, really shallow interfaces instead of trying to make sure that you're accomplishing things all in one particular unit. So let's actually discuss that. So modules should do one thing, but they should do it completely, okay? Your function, whatever your function is going to accomplish, you should make sure that your function encapsulates that logic in itself. You shouldn't ever need to have a string of several functions grouped together in order to achieve a given task, okay? Anytime you have, anytime that is necessary, anytime you have multiple modules that are dependent on one another in order to perform their tasks, that is a red flag. Those modules need to be grouped together into a single module. This means that sometimes your modules are going to become very large, and that is okay as long as it is a simple interface that encapsulates a large amount of complexity. Suffice to say, keep it together. Don't arbitrarily split it up. Alright, moving on. Information hiding. Information hiding was first introduced in a paper by David Parnas, titled On the Criteria to be Used in Decomposing Systems into Modules. Excellent paper. I will have it linked in the description. I highly recommend you check it out. And I just happened to be reading Rapid Development by Steve McConnell, and he happened to talk about this topic, and he had this quote, so I wanted to include it here. A design architect who works for Microsoft said that in 6 years of interviewing more than 200 candidates for software development positions, he had interviewed only 5 who could accurately describe the concepts of modularity and information hiding. And hey, you're subscribed to Howie Code, so you're gonna get to understand what it is. So information hiding is the most important method for creating deep modules. And you can think of a module as a unit of encapsulated knowledge, right? That knowledge should not appear on the interface. The entire point of encapsulating this knowledge is so that the developer who is using this module does not need to know all of the details of the implementation in order to consume it in their application. So the hidden information, the implementation, right? These are the data structures and algorithms related to the mechanism of performing the module's contract. So this is all hidden behind the interface, and a basic example that you probably deal with all the time is SQL queries. The hidden information in this context is all of the implementation details. How does Postgres retrieve the data in an efficient manner that you have requested with your query? All you need to understand is how to go about writing your query. So information hiding reduces complexity in 2 ways. Number 1, it simplifies the interface by allowing the developer to access the complexity of the module through a simple interface. You decrease the cognitive load of your system. And number 2, it makes it easier to evolve the system. So since you have designed your module in such a way that you have very finite and distinct dependencies on which the module will behave, you can be confident that nothing unexpected is ever going to affect the module. And the information that is inside of the module can be handled deterministically. You can think of it as you're not going to have any surprises in there. So any other design changes you make to the rest of your application is not going to affect the behavior inside of your module. And likewise, any changes you make inside of your module should not affect the rest of your system, provided that you are adhering to the contract implied by your interface. So let's talk about when that goes wrong. So when that goes wrong, you have what is called information leakage. And information leakage is when you need to know about the implementation of a module in order to properly use it. So here's an example. Let's say we have a function in JavaScript that is receiving an object, and we expect this object to have specific keys. Let's say the keys are apple, banana, and pineapple, okay? We, outside of the module, we decide that we need to have coconut added to the list of keys. And thus we make this design decision, we change this design, we're now going to be storing this additional piece of data inside of this object, and we try to pass this object into our module, and boom, it breaks the function. The function does not know how to handle this new key that is in there. Okay? In order to properly understand the way that your function was working, you needed to know about the data structure of this object. And because you didn't know that, you broke the module. And that is information leakage. That is a situation where you needed to know about the implementation of the module in order to effectively use it. Let's do another example. Let's say we are implementing a list data structure. If you are familiar with JavaScript, let's say we are implementing the array in JavaScript, right? Now, ideally, when you want to deal with it, you just want to have a push method and a pop method and something to print out all of the contents of it, right? Or something to like find what is at the index of a particular in there, right? These are the sorts of, this is the interface. But let's say inside of our list data structure, we have implemented it as a linked list. And because we implemented it as a linked list, when we designed our interface, when you pass in the item that you're going to insert, you need to have pointers well defined and attached to that. So you need to pass in the pointer to the item that is before it in the list, and you need to have the address clearly prominently available on the item that you pass in, so that way the next push that you were able to do is able to behave in the expected way, right? That is not ideal. That is a situation where the consumer of the data structure now needs to know a great deal about the implementation of it. You should, with this list data structure, be able to have under the hood a queue, an array, a linked list, whatever sort of thing you want, and it should be completely invisible to the consumer of the data structure. They should just be able to perform all of the items on their interface that they need to perform, and your logic under the hood will take care of it however it needs to take care of it. That's the way it ought to behave. That is the goal. So let's talk. This is now my commentary. This is not Ousterhout. This is just me. All interfaces are going to be a little bit leaky. So here's an example. Postgres, fantastic piece of software, but in order to effectively use it, you need to know how indexes work. You need to run an explain command and find out what the results of your query are, how they are behaving, and so on, right? You need to have a little bit of an understanding of what's underneath the hood in order to effectively use it. So it's a little bit leaky. But just because all interfaces are a little bit leaky doesn't mean you can't abandon the effort to make them not so. We want our interfaces to be as unleaky as possible. And ideally, the consumer should be able to just ask for what they want from the interface and receive it as expected. That should always be our goal. Some more caveats. Making a method private is not the same thing as information hiding. And also, information hiding is only appropriate when the information is not needed outside the module. If there is some method that needs to be run in order to do some sort of calculation that's necessary to modify the data that needs to be passed into your module, there's a decent chance that your module needs to be redesigned, but let's say that's not the case. Just make it a public method. Don't hide stuff that the consumer needs in order to properly use your module. Maybe that seems obvious, but the point is just don't take information hiding too far. All right, let's move on and talk about general versus special purpose modules. So general purpose modules can be used in many situations, while special are designed for one specific use case. Generally speaking, if you design your module to be general purpose, it's probably going to be deeper. It's probably going to have a more elegant interface with a more complex implementation. Special purpose modules tend to be coupled to the things that they are being used with, and thus there's a lot of information leakage between the classes. They also tend to have a lot more dependencies with the things that they are interacting with. So, but you also have the situation where, like, if it's too general purpose, then it becomes really difficult to consume. So there seems to be a sweet spot where you're working on solving a particular problem, and you're writing your module, and you write it for your current needs. But as you're writing it, try and conceive of it being used in a general way and design it accordingly. And thus, build your methods inside of your classes for general purpose as opposed to specifically for the purpose in mind. So make the names of the methods general. Don't make it tailored for the specific use case that you're trying to do it for. So this is my commentary now. This is Fisher's fundamental theorem as applied to software design. Fisher's fundamental theorem has to do with biology and evolution. I'm applying it to software right here. The more general purpose a module is, the less suited it's going to be for any given situation. So a very specialized module will be very difficult to use elsewhere. But if you make a module more generalized, it's going to make it more difficult to use in that specific situation. Perhaps instead of having a function that is being called inside of the module, your module now needs to accept a callback function that is going to be called in a specific circumstance, right? That is going to be more cognitively complex. The developer needs to know more about the situation in order to make that work. However, from a system level, if you're able to reuse the same module 20 times because it accepts a callback function, on the system level, maybe it will be less cognitively complex and easier to comprehend the system as a whole. You need to make that judgment call. The last one I want to talk about is what John Ousterhout had to say about testing, because testing is near and dear to my heart. So he comments that you can't imagine doing software without unit tests, and good unit tests allow for easy refactoring of the code. But he does comment on TDD. TDD focuses too much on getting features working and not enough on design. It's just too tempting to hack the next feature and get the next test to pass. And thus, it encourages pure tactical programming. He doesn't believe units of development should be features. It should be abstractions. It should be the center of your thinking should be design, not delivery of the next feature. And thus, it is appropriate. One situation that he thinks that it's appropriate to write unit tests before writing the code is when you're fixing bugs. So you go ahead and you write a test that fails because of the bug, and then fix it so it passes. So this is my commentary on this. I actually generally agree with him. Despite my general advocacy of TDD, I do agree with him that if you're doing pure red-green refactor, only write enough code to make the next test pass, well, you're going to be pretty myopic, and you're not going to be giving a lot of consideration for software design and the system as a whole. And here's where I'm going to say something that's potentially a bit controversial. I don't think red-green refactor is proper TDD. I think this is what you teach beginners in order to show them what test-driven development is. When you are writing your tests, you can write your tests in a way that describe your design decisions and then flesh them out as you progress. One thing that I typically like to do is I will name a test according to what I am looking to accomplish, and I will just start it off with expect true to be false. Just make sure I have a proper test, but make sure that I have articulated what my goal is for the module that I am designing. And then as I develop a better and better understanding of what I am going to achieve, then I will flesh out the test and make sure that I am testing the interface and that the interface is behaving in the way that I desire it to behave. And by the way, this is perhaps the way in which TDD best suits the principles that we're talking about here in this particular video, which is that TDD forces you to think about your interfaces. Okay? Since you are only supposed to be testing your interface, you are not supposed to be testing your implementation, you need to be consciously aware of what the dividing line between your interface and your implementation is and design your unit tests accordingly. Thus, you have a very conscientious understanding of how your system is going to be consuming the module that you are designing. And thus, in this respect, TDD can actually improve your ability to design a well-designed interface, as opposed to hampering it. So that is just my commentary on this, my personal take. I don't think I actually disagree with Ousterhout, and if I do, I am probably the one who is wrong, but this is just an additional take on it that I think informs both philosophies, at least as well as I can. So let's just go over some additional commentary from me. If there's one thing that I can say you want to learn from John Ousterhout and his book, it's that the management of complexity is the difference between a 10x developer and everybody else. This is what software engineering is. The management of complexity, the consideration of the long-term ramifications of the decisions that you are making today. The asking yourself, how maintainable is the code that I'm writing going to be? What trade-offs do I need to make between computer performance and comprehensibility of the code that I have made, and all of the other considerations I need to make? That is engineering. That is our job. That is why we get paid a lot of money. We do not get paid a lot of money simply because we are able to write in a programming language, any more than a great novelist is paid a lot of money because they are able to write in their native language. Here is what is so difficult about this, right? So you go and watch a tutorial on YouTube, or even you pay for one on Udemy, or you read a book or whatever, right? Every single one of these tutorials is going to have you building a relatively small application, something that you can build on the order of hours. Anything that you can understand in a few hours of study is simple enough that you're not going to likely face the consequences of bad architectural decisions. The benefits of strategic programming and not being a tactical tornado are enjoyed on the order of months and years, not in days, which is why when you watch all of these 10-minute videos on YouTube that talk about like why object-oriented programming is so terrible, what they fail to understand is, yeah, there's a lot of boilerplate here. There's seemingly a lot of unnecessary complexity that you can make. You can express the contents of this class that has been written much more simply with a procedural design, right? But what it fails to appreciate is the reusability of that code. The way that encapsulating your modules into classes in that manner to be consumed and instantiated in different locations and different contexts in your application. The amount of knowledge that you save by encapsulating your code in this way. The benefits of that are monumental, but they're also very difficult to measure because they manifest in the form of increased productivity over years, maintainability of your application over years, as opposed to just being able to look at a file and seeing fewer lines of code in the short term. There is research demonstrating this as much. I'm not getting into it here because Ousterhout doesn't get into it, but I'll get into it in another video that will talk about the importance of code quality and the actual scientific research that has been done in that regard another time, because that deserves a video of its own. But suffice to say, I'm not saying that object-oriented programming is the be-all, end-all. I'm just saying that anything that you're going to learn from a 10-minute YouTube video is probably not going to sufficiently express to you the necessity of the system-wide considerations here, the architectural decisions, the consequences of the bad decisions of not encapsulating your code and not achieving good information hiding and modular design. It's something that you can't understand until you see the negative consequences of not doing it that way on applications that are like, I don't know, 2+ years old. Another thing that makes this really hard is I can't just give you a list of best practices. I can't just tell you how to do strategic programming. Follow these procedures, follow these best practices, and you will be a 10x developer. That's just not how it works. The way to become a truly competent, a truly expert level programmer, at least my understanding of it, is to constantly be making these evaluations of what is the simplest solution I can make with the tools I have available for my problem that I'm trying to solve right now. If I'm going in and I'm just taking test-driven development and throwing it at the problem and doing what that tells me to do, if I'm just reading the React docs and say, hey, you should do this, okay, I'm just going to do that, or if I'm just copying, like, I don't know, the latest hotness, the latest framework, right? You're never going to get beyond advanced beginner level of skill. You always need to be pushing that boundary, and you always need to be thinking How do I engineer this? How do I manage complexity? How do I get the smallest number of dependencies in this module I have designed as possible? And how do I design an efficient module such that it adequately meets the needs of my specific use case, but it can also be reused in additional locations so I avoid writing additional code and thus increasing the total cognitive complexity, the understanding that a future developer needs in order to maintain this thing that I have created, right? That is the challenge, but that is also the fun, and that is what we need to learn. There's another caveat I want to add about strategic programming. So, tactical tornadoes are not the only dangers to architecture. If you are taking the latest cool design pattern that you learned, the cool new method, like, oh my goodness, really good developers write publish subscribe models, right? And so I am going to use a pub sub to make a list. I am going to use a pub sub for everything because it is the best design pattern. After you have written the code, after you have made a change, is it actually simpler? Is it actually easier to maintain than it was before? And I always like to go to Plogger's quote on this. The name of the game is congruence. The techniques you employ had better be consistent with the intrinsic complexity of the problem you're trying to solve. You should write the simplest code that you can for the system that you are trying to design, and nothing more. So here's my bibliography. This is a talk that Ousterhout gave for Google. Fantastic. And it is also just his book, A Philosophy of Software Design, my favorite book on software. I highly, highly recommend it. Once again, my name is Howie Reith. If you have questions, please feel free to leave comments. You can also feel free to contact me at howard.reith@gmail.com. This is a huge topic. I really hope this was helpful for you. It's something I'm very passionate and enthusiastic about. In case it wasn't obvious, this is thinking about this stuff is my favorite stuff in our profession. So I hope this was of value to you. Best of luck in all of your design decisions.